In this question, we're told that we've got a smooth concrete pipe and we need to find the diameter of that pipe so that it will transport 0.002 meters cubed per second of water over 400 meter length. And we're also told that the pressure drop should not exceed 2.94 bar, and we're also given the fluid properties of water. So how do you go about solving this? Well, because we've got the flow rate and the pressure loss effectively, or the pressure drop, we don't know the diameter, and therefore we can't find the Reynolds number in the pipe, and we also can't find the relative pipe roughness. So this is a type 3 problem where we don't know the diameter, so we can't find, as I say, Reynolds number or relative roughness. So we need to make an assumption to start the problem. So if you remember, we assume a friction factor, calculate a new diameter, recalculate all the parameters to get a new friction factor, and keep iterating until we get to the solution. And the friction factor that you start off with, or assume for these type 3 problems, is a friction factor of 0.03. And you'll see why when you look at the Moody chart, because it's pretty much slap bang in the middle of the Moody diagram, and then we can kind of iterate around this point. So we choose a friction factor of 0.03 for this problem. So from our Darcy-Weisbach equation, we have the pressure loss, which is the pressure drop that we mustn't exceed. That's equal to friction factor times length over diameter. So we know the length, we're trying to find the diameter, we know the density, but we don't know the velocity. However, we are given the volumetric flow rate, and we know the velocity is linked to the volumetric flow rate in terms of the area. So we solve to find velocity, but in here we got velocity squared, so we square everything. We also know that the area is a function of diameter, which is something we're trying to find out. So working out the area, substituting into this equation, then we end up with the velocity squared is a function of the volumetric flow rate and the diameter. So now we just substitute this into this equation. So this is what we had on the previous slide. We had the Darcy-Weisbach equation and the velocity squared that we'd worked out as a function of the volumetric flow rate and the pipe diameter. So substitute that into here. Now the only thing that we don't know in here is the pipe diameter. We know the friction factor, the length, and the volumetric flow rate. So rearranging for diameter, we end up with this nasty root to the power of 5, but it's just where it is. But you can solve know everything in here now. So if we put in the values that we have from our the question, but first, before I do that, what I'm going to do is, because for each iteration the pressure loss or pressure drop won't change, neither will the length, neither will the volumetric flow rate. It's only the friction factor that's going to change from iteration to iteration. So just to save a bit of time, I'm just going to work out all this as a kind of constant, and then just times it by f each time. So you can do that just to save a bit of time. So that's what I've done there, is just put in all the values, and this is my kind of constant. And then I'm going to work it out the diameter from changing the friction factor each time. So starting off with the initial guess, as I said, which is in the middle of the Moody diagram with friction factor of 0.03. Then our first guess at the diameter is 0.042 meters, or 4.2 centimeters. So now we have a diameter, but obviously we just made that on a complete guess. So we need to kind of check if this is right. So we need to work out the Reynolds number and friction relative pipe roughness to see where this puts us on the plot. So once we've got the diameter, we can work out the velocity from the volumetric flow rate. That gives us velocity 1.4 meters per second. That then allows us to work out the Reynolds number, which gives us a value of around 60,000. And we can also work out the relative pipe roughness. Remember, in the question we're told that the pipe is made of concrete, so we know what the roughness is of that, or what the typical value is from the Moody diagram, and then we just divide through by the diameter. So that gives us our relative pipe roughness. Now that gives us our first guess on the moody. Sorry, this was our first guess on the moody diagram here, but now plotting our kind of second values. So we worked out the Reynolds number to be 60,000 or 6 times 10 to the 4, and our relative pipe roughness. So here we are. We look at the Reynolds number and then find the relative pipe roughness. So we're following this line, and that puts us here. So that we've moved from our initial guess to here on the diagram. Okay, so from this we can now read off a new friction factor, which from the graph is 0.021, or if you do it mathematically using the equation for those lines on the Moody diagram, you see a very slight increase. But you know, for the accuracy that we're interested in, either of these values is fine. So we now have a new friction factor. So now we need to calculate a new diameter. So using this equation that we had before, put in the new friction factor. Okay, so remember I worked out this as a constant. Then we get a new diameter of around of 3.95 centimeters. So now we've got a new diameter, so we now need to check that this value is right. So from our new diameter, we calculate a new velocity based on the volumetric flow rate, and that gives us a velocity of 1.632 meters per second. That allows us to calculate a new Reynolds number using all the new values that we have, which gives us a new Reynolds number around 6.45 times 10 to the 4. We can also calculate a new relative roughness from our new diameter, and then we can look at on the plot to see where this is. So this was our first guess. This was our second guess, if you like. Then if we plot the third value we've got, so the Reynolds number hasn't changed much, it's 6.5 times 10 to the 4, and the relative pipe roughness hasn't changed much. So we're about here on the plot now, so you can see it hasn't moved fast, so we started to converge on the solution. So we read off our new friction factor, which as you can see hasn't changed much from the previous values. 0.021 last time, it's now 0.022. Again, either can do it from the graph or by calculation. So we take that new friction factor and calculate a new diameter, and we come out with 3.95 centimeters. So therefore there's no change in diameter from the previous iterations, therefore we've converged to our solution. Now the question asks for the diameter to the nearest centimetre, so therefore we need to round this up so the answer is 4 centimetres. Now just one word of warning, I guess, here is obviously, you know, if you were asked to round that to the nearest centimetre, mathematically you would, you know, say it's greater than 3.5, so therefore round it up to 4, you know, get the correct answer. But just be aware, had this, for example, come out as 3.1 or 3.2 centimetres, now naturally you might have tried to round that down to 3 centimetres, but actually that would have given you a wrong answer, because remember, this is the diameter that you need to give you this pressure loss or this pressure drop. So if you decrease the diameter in a pipe, you increase the pressure drop across it. So the fact that 3.1 centimetres might be closer to 3 centimetres and 4 centimetres, you should always round up in these instances, because then that will give you the larger pipe diameter, which will give you the lower pressure drop, so therefore it won't exceed what the requirement pressure drop is. Okay, so here we rounded up to 4, which makes sense, but had that been 3.1 or 3.2, we would have still rounded up to 4 centimetres.